Here's the slitter rewinder edge guide control refit. Here's the machine. The stock roll there is drawn through the machine. The output roll is there, and the slitters are here. The edge guide, the purpose of the edge guide is to feed back the edge position or regulate to this null point, this little white line, and servo this rack to keep that edge aligned through the machine. This sensor has a sensitive region of about 1/8 of an inch either side of the little white mark, and it saturates -10 +10 volts left and right. That feeds back to this analog input module here, -10 to +10. That's the position feedback. On the lateral rack that drives the stock roll side to side, there's an LVDT. That's 4 to 20 milliamp. We're taking it as 0 to 10 volts, or 3 to 10, 3 to 8. Again, into this analog input module. The web speed, the speed of the paper, is estimated off this idler roll with this optical sensor. There's a reflector, so we get a pulse count. Given the diameter of the roll, we can estimate the web speed, and that feeds into this counter module. And we drive 0 to 10 volts out to a Wanfla hydraulic servo valve amplifier. No flow, 5 volts, 5 to 10 drives it one way, 0 to 5, 5 to 0 drives it the other way. So our command is bidirectional, about 5 volts. So that logic, our control loop is implemented in this P1AM100 from Automation Direct in C. A couple other things of note: we have a gain scaling potentiometer, nominal 50%. We can have or double the design gain. Master on switch. Below 50 feet per minute on the web, we zero the gain. Only above 50 feet per minute do we activate the controller. Now, the other thing that the speed provides is a gain scaling within the controller implementation to account for the transport lag between the paper leaving the tangent point when it threads through, comes off the top. So we have some tenths of a second, depending on operational speed, which is typically 200 to 1500 feet per minute between that tangent point and the point of interest. The implementation is essentially two-state feedback on the rack. So we consider this as a loosely coupled position feedback of the rack. And when we sample the LVDT and numerically differentiate that and take that as the velocity feedback or the rack speed. So you can think of it, we have X and X dot. And we close the loop. We have two loops. It's essentially like tachometer feedback on a motor control application, an inner loop tachometer feedback, outer loop position feedback, with the added complication that we have this transport lag in the system. Now, given the precipitous phase decline introduced by transport lag, the control design starts with a nominal crossover and gain based upon the plant dynamics or the plant model that we've identified. We select a crossover frequency, open loop crossover, and a gain for that condition. Then we look at the range of speeds, which produces a range of time delay. And in the frequency domain, look at that range of phase degradation. And based upon our speed estimate or measurement, we scale our gain. The nominal design, if we had no transport lag, would be an incredibly sluggish lead zero that given this a type 1 plant, and we have an integrator implemented in the controller at our design crossover, we've designed for 85 degrees of a phase hump. And that makes it a very slow design on paper. Pardon the pun. However, when we introduce the phase lag due to transport lag, the gain scaler seeks about 50 degrees of phase margin at the scaled crossover, the crossover frequency, open loop crossover frequency for the scaled gain. And you'll see that in the models, in the estimates, but that gain scaling is being driven by this speed, and we essentially take back that large phase hump that we introduced with the very slow zero and the paper design, and are able to then operate this over the range of speeds. This is implemented in C on an Arduino-based programmable logic controller. It's being driven by a timer, so we have a tight timing control or pacing of our control loop at 100 Hertz. Some other features of note, we have the edge guide, the ultrasonic sensor amplifier or conditioner is here. We drive, we power everything off the main 120 volts, 110 volts from the main rack. And we'll see it operating here shortly.